Hi and welcome again to my science channel. Today we're going to have a look at another type of passive component. Previously we've looked at resistors, but what we're going to have a look at tonight now is capacitors. So capacitors, they've been in use for quite a long time now, and in fact it was possibly said that the Ark of the Covenant was actually a massive capacitor. Then you had guys like Benjamin Franklin used to go, I'm sure you've seen the pictures where he was flying kites in the thunderstorm trying to catch lightning bolts and to save and store the charge, and that charge would have been stored in Leyden jars, and all a Leyden jar is a glorified capacitor. And the definition of a capacitor is two conductors separated by an insulator. So let's have a quick look at that. So the symbol for a capacitor is going to be like that, and as you can see you've got two conductors separated by an insulator, or these are also known as plates. And this insulator has a very specific name in the middle, and that's called a dielectric. And this is the symbol for capacitor, as we said, and sometimes a capacitor will have a plus on it. And if it's got a plus on it, that means it's usually a kind of electrolytic capacitor, which we'll have a look at in a minute when we have a look at capacitor types. And that means it's polarized. So you've got to have it connected the right way around, because if you don't, things will start to go bang and make lots of smoke and sparks. So we've got to connect that up properly. So that's the dielectric, and as we'll come to see later, the capacitors are named after the dielectric type. And another thing we can look at in capacitors is the amount of charge it gets. So Q is our charge is equal to C times V. So Q is the charge in coulombs, C is the capacitance value, and V is the voltage. And that will tell us then what the charge on the capacitor is going to be. What kind of capacitors do we see in the real world? Well, these ones here are ceramic, and the names of the capacitors will be taken from the material that separates the two plates of the capacitor, or the dielectric, as we've already said. So these are ceramic ones, and you get these into real low levels of farads, or microfarads in fact, which are millionths of a farad. These ones are polystyrene. You don't see those so much now, but they are still about in one or two places. More difficult to come by, but very accurate capacitors. Now this type of capacitor, which is the electrolytic, is polarized, so it's got to be connected the right way around. What we can see here is the axial one, so the leads go into the capacitor and out of on either side, and the radial. These are both electrolytic capacitors, and this one is radial. As you can see, the leads just come from one end, so that's radial and axial. These two are pretty popular as well. This is a bead capacitor, and this is a tantalum capacitor, so the dielectric material is tantalum, and this type of capacitor is polyester. So those and those are all pretty much run-of-the-mill. You see them all the time, whereas you don't see the polystyrene ones so much. So we've talked about a capacitor holds charge, so let's see if we can demonstrate that. So what you can see here is my little multimeter, and we'll set that to resistance range. And then what we'll do is, first of all, we'll get the axial capacitor, which is quite a large value, which is 1000 microfarad, and we'll pop that onto it. And if we pop our leads on, what we should be able to see is initially you've got a current flow, and then very slowly you can see the current decreasing. This is measuring resistance, so it's passing a tiny current, and you can see as the capacitor is charging up, the current is diminishing. So you can see the capacitor slowly charging, and you can use that for a capacitor test as well. And now the radial capacitor we have here, that's a lot smaller value of farads, and so if we connect that, what we should see is a very much quicker charge, because it's less capacitance to charge, and you can see that going down quite quickly as the capacitor is charging up. So while it's doing that, it's accumulating charge, and then hopefully we can see if we select a milliamp range or microamp range, then we should be able to see that discharging. Or you can see it's holding that charge there that is taken from the meter. Okay, so we've seen the types of capacitor there, and we've demonstrated that it can hold charge. So what we'll do in a moment is we'll have a look at how these capacitors charge up. I'm going to talk about the time constant for a minute. So our capacitor, we're looking at a circuit here, very basic. We've got a 9-volt power supply, a 15 kilo ohm resistor, and a 470 microfarad capacitor. And that resistor is going to help control the flow of current to here, so it will control the rate that the capacitor charges up. And so with that in mind, we've got the time constant for the circuit. The time constant, the Greek letter tau, is equal to R, which is the resistance, multiplied by C, which is the capacitance. So tau is going to equal 15 times 10 to the power 3, because it's 15 kilo ohms, and 470 times 10 to the minus 6, because it's 470 microfarads. So if we work that out, that gives us a tau value, or a time constant for the circuit, which is equal to 7.05 seconds. Now, the value of tau will be the first value, the first time constant. It will tell you when that capacitor is charged to about 63% of its full capacity, but this is not a linear charging. So for the capacitor to be fully charged, we can say it's fully charged within 5 time constants. And for 5 time constants on this is 7.05 multiplied by 5, which is 35.25 seconds. So for this circuit, we can say that that capacitor is going to be fully charged within 35.25 seconds, which is 5 time constants, as we've said. Now, I've set up the circuit here, and what we're going to do, we're just going to do a little bit of an observation on how this capacitor is going to charge over time. Okay, so we've set this circuit up. Here's our 9-volt power supply. Here's our capacitor, electrolytic radial. So of course it's polarized, so negative to the negative, positive coming across here through this resistor, which is 15K. You can work that out by the color bands, brown, green, orange, and you can see that on my other film as well if you want to know how to work those out. And then we've got a switch here to enable us to switch on and off at any time. Essentially, what we're going to need as well is our voltmeter. We need to measure voltage at particular intervals on this, and we're going to attach a negative lead and a positive lead. So what we're going to do now is we're going to measure the voltage across this capacitor, and we're going to fill in this time table. So we're going to measure 5 seconds, 10 seconds, 15, 20, 30, 40, 50 and 60 seconds, just to see how this is going to charge. And then what we're going to do is we're going to plot the results on this graph here. So what we're going to do is, as we measure the voltage building up on the capacitor, we're going to measure it 5, 10, 15, 20, 30, 40, 50 and 60 seconds. And then what we're going to do is plot that on this graph here. Okay, so first of all, we're just going to short out the capacitor just to make sure there's 0 volts on there. So I'm just shorting the 2 leads together, and we've got 0 volts. What we're going to do is we're going to do a time charge on this now then. So I'm going to give it 5 seconds, and here we go, 2, 3, 4, 5 seconds. After 5 seconds, we've got 4.31 volts on it after 5. So we're filling that 4.31. Okay, so what we'll do now is give it another 5 seconds and see where we go there. One, 2, 3, 4, 5. So after a further 5 seconds, bringing it to 10 seconds, we've got 6.33 volts. Now we'll give it a further 5 seconds, taking it up to 15. 2, 3, 4, 5. So that gives me 7.49. What I'll do now, I'll pause the film for a second. I'll finish off taking these measurements. I'll plot the graph and then we'll discuss them when that's done. So here's the results we plotted at 5 seconds. As we said, it's going to be 4.31. But note this, it's not an even chart. So 10 is 6.33, 15 7.49, 20 7.9, 30 7.97, 40 8.82, 50 8.87 and 60 8.9. So plotting these on the graph, we can see that the curve has this kind of shape, and that's got a very special name to it. That's called an exponential curve. And so the growth is exponentially growing. So the voltage is exponentially growing. And we have ways that we can predict at what sort of time on this curve the voltage is going to be. We have a very specific method of being able to calculate the voltage on this curve at any point in these times. So in a second we're going to have a look at that, but just to verify that calculation, what we could do is I'm going to charge this capacitor for 4 seconds. So what we said was we're able to predict the voltage across the capacitor at periods in time using an exponential function. So this is our exponential there, E. You could consider it as being E for exponential or E for Euler, and it was Euler who discovered this constant back in about the 16th century, I think. And that tells us that voltage on the capacitor is equal to the voltage on the supply multiplied by 1 minus E to this up here on top, which is minus T over RC. So V capacitor, V supply, T is the time elapsed. So we're going to use our 4 seconds to see how that went, because we said after 4 seconds our voltage on there was, after 4 seconds, is 3.7 volts. And we're going to use this to try and predict that. So we say V capacitor, if we start putting our numbers in, V supply is 9 volts. 1 minus E to the minus T, so we're going to say that's 4, because it was after 4 seconds, minus 4, divided by RC, which is the resistor value and the capacitor value, and that's our time constant. So that's going to be, we calculated that out as 7.05 seconds. So if we work out that first, voltage over the capacitor equals 9 brackets 1 minus E, and if we work out that, so minus 4 divided by 7.05, that would give me E to the minus 0.56. So we should be getting there slowly now. We're building up our equation. So VC is equal to 9, 1 minus, and E to that number is going to be, so E to the minus 0.56 is going to be 0.571. So now we're really starting to get somewhere now. So V is equal to 9 times 1 minus 0.571, that equals 0.429. So VC is going to be 9 times 0.429, 0.86 volts. So calculating that after 4 seconds, it comes to 3.86, whereas we said 3.7. So that's pretty close. So why isn't it actually bang on? Well, I'll show you. We're wondering why the numbers were bang on when we calculated 3.86 and we actually measured 3.7. So obviously you've got tolerances in the meters first of all, but we're working in an imperfect world. So we were assuming the battery was at 9 volts, but let's have a look at this. So the battery is at actually 8.9, so that would have an effect. And then also electrolytic capacitors like this are notoriously sort of inaccurate. They've got quite a large tolerance on them. If we look at the value, we've already said that it's 470 microfarads. So if we go to microfarad, so if we measure it, we measure the value, and we measuring at 448 microfarads. So that's another reason why it could be out, because of the tolerances in electrolytic capacitors. So that's a little bit about capacitors. We've talked about the construction, we've talked about the different types, we've talked about the charging, we talked about the exponential charging of it, as well as the charge held, which is coulombs, Q is equal to CV, and then we've performed an exponential calculation. So I hope you really enjoyed that. I've enjoyed doing it for you, and if you want to, comment and subscribe, and we'll see you next time. Thank you very much.